ahead and start recording, would be the dissolving sugar and the dissolving salt. Because those two start with very similar things. We've got a clear liquid and a white solid. We dump the white solid in, it disappears into the clear liquid. We could drink the clear liquid and it tastes either salty or sweet. So we can pick up those distinguishing factors. What makes this example more interesting, in my opinion, is the dissolving sugar ends up coming out as what process did we decide? It's a physical change versus the dissolving salt was the chemical change. Really the only way that you would be able to distinguish between those being a physical and a chemical change is if you knew something about the properties of each of those compounds, okay, in particular the bonding structure and what's happening during that process. How can we expect you to be able to know that difference day one of a chemistry class, introduction to chemistry class? And if you go online and look up, is dissolving salt chemical or physical, you'll find that everybody has their own freaking opinion on what it's supposed to be it physical or chemical. Okay? And to me, one of the biggest issues is that we've set this up as it's either chemical or it's physical. And it's not really that circumstance. It's more like a rainbow, which would have been nice if I'd colored in here, but how do rainbows go? Where do they go? Red, orange, I don't have yellow, green, Roy G, blue, I don't have indigo, and there's violet. So there's our first approximate rainbow. When we look at that rainbow, we don't say it's just those colors. Remember, the rainbow is a composition of all colors. Okay? How do we know we're at red versus orange? Someone came in and dropped a definitive line and said arbitrarily, this is red, this is orange. That was a human invention on the color spectrum. Same thing is happening with physical versus chemical. Okay? There is no definitive line between them, but there are some things that are more of a physical change and some things that are more of a chemical change. To determine exactly where that difference is, you pretty much have to know specifically what's happening in each of those processes. And that's not the easiest thing, at least for an introductory chemist to come up with. And I would argue even for more advanced chemists to actually decide what's going on between them. Okay? Because in general, if you ask, feel free to ask any friend that you've had that's had chemistry and ask them about dissolving salt. You'll probably see a pretty even mixture between some of them saying chemical and some of them saying physical. And that's because the dissolving phrase tends to be associated with a physical change, not a chemical change. All right? So the question is, well, why would I bring this up? I want to bring it up because science isn't perfectly black and white. Okay? There's a lot of gray areas, and those gray areas are usually the areas that students hate because it's a lot more effort to memorize and figure out what's going on within those ranges. Okay? So we will talk about chemical and physical, and you will see them show up on exams. Okay? The questions that I will ask will be, at least initially, will be the very clear differences. Melting water, okay? Burning wood. Those are things that classically students seem to understand as melting water being a physical change and burning wood, chemical. Okay? Both of them are ultimately taking some, they're not both solids, but burning wood, we're taking a wood, taking it up to the gas phase, and melting, we're taking a liquid and taking it up to the gas phase. So both of them are a transition to the gas phase, but we're doing a different process in each of those cases. Okay? Does that mean you won't ever see the dissolving salt or dissolving sugar show up on a test? I might throw it in there because we've now spent 2 lectures talking about them. Right? So it is something that we've discussed in class, and students that have come to class should be aware of what those differences are in each of those cases. Do you agree? Do you now know that dissolving salt is a chemical change? Okay? Getting some head yeses. Okay? I can accept that. Okay? And that dissolving sugar is physical. Yeah. Okay? Since we've discussed it, I think that is a fair question to ask. Based solely on what the textbook told you? Yeah, you're right. That's a bit questionable to ask. Right? When it comes to the homework, these gray area things, I'll try and keep the gray areas out of the homework so you get the clear black and white for practice. Okay? Make sense? Did I make you more nervous or less nervous about your question? Right in between? The color image in between, I think I talked about where that came from. That was actually a project that I was hoping to have students do in the organic chemistry lab, but I couldn't get it to work. The idea was to make the compound that does that, and what it does is it literally changes color because it changes its structure. And we end up having a chemical process in that change because the structure changes. How do you know because the color changed that the structure changed? Well, are there other cases where color changes and we don't have a structure change? Yeah, so how do you know? Really, you don't. Okay, you have to get kind of told each of these comparisons. Does that suck? Yeah. Sorry. That's what it is. Okay? Questions about our chemical versus physical? Okay. So we can now move into the energy section of chapter 3. They've got some pretty pictures on there, and I've added some others. We could fire a cannonball, and what we've got is a balance between potential energy and kinetic energy. We won't talk about that too much because there's another class where you would see potential and kinetic energy. That class being, anybody know? Physics. Physics looks at the balance between potential and kinetic energy. Potential energy is something inherent to that molecule or structure at a particular point. Okay? There's no motion associated with it. It's how much energy is stored in that situation. So if we look at the the potential energy for our cannonball is at its maximum, okay, at the highest peak, okay, right before it starts to turn and come back down. And what ends up happening as that cannonball falls is all of that, or a lot of that potential energy gets converted into kinetic energy, okay, which on its own isn't that big of a deal until, say, you got hit with the cannonball. And then what happens to all the kinetic energy from the cannonball? It gets converted into the kinetic energy of your body, which is not particularly pleasant at that point. Right? So we're looking at how this energy can get transferred through different processes. Right? We could look at an engine, looking at each of the cycles of an engine, combustion engine. So we've got the individual pistons. We can have an intake of gas, okay, or particular gasoline. When we combust that releases the chemical potential energy, the energy stored in the structure of gasoline. It releases that energy, which then causes the piston to move, okay, or get powered in a moving cycle. And we take that conversion from chemical into physical energy or mechanical energy to allow our cars to move. Okay, kind of a neat process. This is even further shifted into, say, biology and all living life as we really know it, most of it. We've got ATP to ADP. Any biologists? What does ATP stand for? Adenosine triphosphate, and we look at the conversion into adenosine diphosphate. What's happening in that process? Well, we went from a triphosphate to a diphosphate. It's pretty much the same thing as combustion. We are breaking or releasing the energy in a phosphate group. We break a phosphate structure off of ATP. That release or that breakage of that bond releases energy, and then as living life forms, we can take advantage of that energy release and allow us to do different processes. Yes?
So is that chemical? Is that mechanical energy? Or?
So in the ATP to ADP, that's chemical energy. It's all strictly chemical. So energy can be fun to play with. All right, so let's take a look at kinetic energy, temperatures, and physical states. All right, so we've got solid, liquids, and gases. All right, we've got images down below. Which one's the solid? One on the left, I can accept that. So we've got a solid. What's the next one? Liquid and gas. How do you know that? Okay, we could look at how the atoms are arranged. Okay, we could remember back to when we talked about the different phases of solids, liquids, and gases. okay, in their relative compressibility. We looked at the solid. Can we compress that solid structure anymore? No, why not? What happens? The spheres end up butting up against each other, and we can't compress that phase. There's a little bit of white space in there, so we might be able to compress it a little bit, but not much. What about the liquid? We got a little bit more white space, okay, dead space between those spheres, so we can potentially compress a little bit, but again, there isn't a whole lot of compressibility. What happens to the gas? There's a lot of white dead space. So what we can do is take that gas box and shrink it down and really compress the volume that's holding those. So we could apply our understandings of our solids, liquids, and gases, or those phase materials, to come up with what these definitions are. We could also use our understanding of kinetic energy. So at any given temperature, which one has the most kinetic energy? Okay, so gases have the most kinetic energy. What does kinetic energy most easily equate to? We convert that into a less scientific term. Movement. The more movement a particle has, the more kinetic energy. Okay? So if we go back and look at these, we would expect the gas to move the most, so it's going to have more kinetic energy than the liquid. Okay? Compare the liquid to the solid. Which one moves more? Liquid. So which one has more kinetic energy? Liquid. Okay, so least and our most kinetic energy. So do solids have no kinetic energy? That one becomes tricky. Okay, and don't think about running up, oh, I can push every object. Okay, let's not translate any kinetic energy into them. Let's just take a table. This table sitting on its own, does it have any kinetic energy?
Yes.
Where is that energy? It's not moving. Okay, why does it have kinetic energy? Has mass, we could look at that. What is moving within this table? The atoms and molecules that make it up. What makes up atoms and molecules? We could look at all the subatomic particles, our protons, neutrons, and electrons. All of those are constantly moving. Because they make up the table, all of their kinetic energy adds to the overall kinetic energy of the table. Okay? Is that significant at our scale? No. Why not? What's the mass of a single electron, proton, or neutron? So tiny that that kinetic energy contribution isn't something that affects our overall interpretations of it. Okay? Is it something that's incredibly important to the structure of the atom? Yeah. Which is what a lot of science, at least current science, is now based around, is looking at the energy of each of those particles and trying to understand how that can contribute to our overall world. Okay? Or how can we can scale from that really, really tiny quantum level scale up to the macro level scale that we see now. Okay? So it's kind of a neat process. Next question to bring into this is what happens when we change our temperature. Why? Okay, as we increase the temperature, most particles tend to move more. Okay, I know it seems kind of counterintuitive, at least to me, because if I get heated up, I'm not going to move very much. Okay, I tend to slow down. But we could look at it as an opportunity to find some other place. So if I start to heat up, what ends up happening? Do I just sit in the heat? No, I move away from it. I do pick up some kinetic energy and I try to get away from, lose some of that heat. So we do see kind of an increase in heat and an increase in kinetic energy. Same thing happens with each of our phases. Let's increase the temperature on a block of ice. Let's start at -4 and move up to 0 degrees Celsius. Okay. We do see an increase in kinetic energy. Okay. We may not visually see that, but more energy is being absorbed by that ice. Once we hit that 0.5 degree Celsius, what happens? It starts to melt. Okay, why is it melting? we've given each and every single one of these spheres enough kinetic energy that it starts to move more. And we've now transitioned into the liquid. What happens as we continue to add energy to our liquid? They're going to continue to move more up to the point where it evaporates and transitions into the gas. Can we continue to add energy? Yeah. We can continue to add energy ultimately, indefinitely, and these particles will keep moving, okay, and keep moving faster and faster. All right? So we have this strong correlation between kinetic energy and our individual phases, which is kind of a neat process. Okay? So the next thing we can do with this is we want to have some kind of constrictions on this. So someone was convenient enough, went through and kind of evaluated each of these processes and noticed that we have a conservation of energy. We can't create it, we can't destroy it. This is looking at our laws of thermodynamics, again, from physics. Remember, chemistry is a pretty hardcore crossover between physics and mathematics and our real world. Right? So we can convert our energy from one phase to another, but I can't destroy it. Okay? So if we looked at the potential energy, that particle or that cannonball has that energy. Okay? And at that peak, it has no kinetic energy. But as soon as I let go of it, what happens to the potential energy? It turns into the kinetic energy. Okay? So I'm allowed to convert from one form to another, but I can't destroy it. So the potential energy may go to zero, but the kinetic energy goes back up to what the potential energy was. Right? So the sum total of all energies within an individual system can't change. But what we can do is convert from the different types of energy in between them. Okay, so we need to know what the different types of energy are. What are some examples? What's that? Heat is a good example. Okay, that's actually probably one of the more important ones. It's actually why we don't get perfect energy transfers. We've already talked about a couple of the others. ATP to ADP was the release of chemical energy. Where else do we have energy? We've got electrical energy. We could look at the outlets. Okay, I'll keep reference. We'll probably do that more in organic chemistry. We don't stick our finger into the outlet because there's a lot of energy in there and we don't want that pumping into our body. Okay? I'll stop making you guess. So we've got 6 different primary forms of energy. Okay? Some of them have slight overlaps. We could start to compare them in different situations. Okay? So heat, light is a form of energy. How might we know light is a form of energy? Photosynthesis. Okay? The sun produces this energy, or some light. If that wasn't an energy source, what happens to our plants? They die. They don't have any energy. Okay, so what are our plants doing to that light energy? They absorb it and convert it into food, which is chemical energy. What do we do then with that chemical energy? Okay, that's looking at our ATP and ADP. We can consume it as humans, and we're keeping it in form of that chemical energy. What else do we do with it as humans? We heat it up to do what with it? Okay, we could cook it, but then that's again our consumption. What do you mean store it? Okay, that's still looking at just what humans as animals do. Don't we, as humans, do something else with all this plant mass? We burn it. And in the process of burning it, we typically take that heat energy released and use that to boil water, which then does what? Yeah, it turns into gas. It powers turbines. What do the turbines do? Convert that chemical energy that we took into heat and turn it into mechanical energy or even electrical energy. We convert the mechanical into electrical. So we've got all these transitions all the way through so that we can have lights in our room and convert it all the way back to light energy. All right? So all of those individual processes get tied together through what we end up doing. The last one, okay, we can look at the nucleus or what makes up individual atoms, and we can try and control that energy. What do we as humans do with that? You think, oh, it's fancy, we gotta use that. What do we do with our nuclear energy? We use it to boil water, to convert it into heat energy, which then converts into mechanical energy, which then converts back into our electrical energy. Okay? So we're looking at each of these individual steps through this process. If we can come up with some way to shortcut some of those, maybe we can actually get a more energy efficient system. Okay? Questions? So, energy and chemical changes. This was an old slide. I think it's in your textbook. Thought it was kind of boring, and I was going to do an example of it in class today, but I couldn't quite get it to work the way I wanted to, so we'll watch a short little video about it. We can take water and pump a bunch of electrical energy into it. That electrical energy can cause the water molecules, our H2O, to split. We can cause our water to split into molecules of hydrogen gas and oxygen gas. And we look at our electrical energy, we have a ground and a neutral, so we end up having two poles associated with it. Turns out our hydrogen will form at one pole and our oxygen will form at the other. How could we prove this? Well, we could then collect the gas that comes off of those poles. Okay, it won't dissolve in the water. And we can then play with those individual gases. Hydrogen's kind of fun to play with because, what's that? It's flammable, yeah. It will combust with oxygen, and depending on the environment, will give you a nice big boom, okay, which was partly one of the things I wanted to play with, but we don't have a blast shield, and we've got sprinkler detectors or fire detectors in here, so we want to be a little bit careful with that. So we might get to play with that example in lab. Let's see. Will this actually work? Okay, this guy is thoroughly exciting, and I know you would love to watch him in more depth, but I'm going to skip ahead a little bit here. So what we've got is a beaker of water. He's put a couple different electrodes in it and put test tubes over the top of it. Come on. And he's got it attached up to a power source, which is that big blue box. You can actually do this with just a battery. And when he turns that on, eventually, he's a little slow, but because he wants to tell you about it. If you look very carefully, you can actually start, well, not so carefully here, you can actually see gas form off of this. Okay. Turns out, based on, he's really excited about it. The stoichiometry of that reaction, so how much hydrogen versus how much oxygen is produced, hydrogen will get produced in a much larger amount. You can see a volume difference. Okay, so we could try and determine that way our law of compositions or definite compositions. How do these things come together? How do we decide which test tube is which? Well, we may need the volume for this.
Is hard. The gas
It's
is
really
hot
exciting.
like hydrogen.
Listen. That was it.
Test two. Light the wooden splint.
So when you have that small of an amount, you're not going to get a big pop. But that little kind of, I don't know how to describe it, that little sound is the hydrogen combusting in this case. If you go through and take oxygen, he extinguished the fire, so just had it hot enough and put that into the oxygen tube. Well, oxygen facilitates combustion reactions. So if we put out the fire and then give it tons of oxygen, we end up seeing it reignite. Okay? So we'll go ahead and stop that exciting video. Let's see if I can do this neatly. That worked. Okay? If you do want to try and play around with that at home, you can talk to me or go on YouTube. There's tons of YouTube videos that explain how to do it as well. All right, so let's take a look. Some of people have probably already heard of this. In terms of how much it's going to cost you, okay, as the individual consumer, when is it better to fill your gas tank? Okay? When it's cold in the morning or hot in the afternoon. Okay, how about you share with the people around you for a second? Everybody got real quiet, so I guess you're done talking. What's the answer? It's cold in the morning. Well, if it was cold at night, we could do it at night too, but we want the cold. Why the cold? So it has to do with the density of the gas. Remember, as we add heat energy, what happens to the individual particles? They spread out. They move more. Okay? We're still in a liquid phase, so don't get me wrong, you're not pumping gasoline into your car. It still is a liquid. But as we give it more energy, it starts to move a little bit more, which means that same mass of gasoline expands and fills a larger volume. How does your car measure gasoline? By volume. So if we go when it's a little bit colder, what happens? We get more mass for the gas. We save a little bit more money. How much of a difference is that? Well, how much does our liquid compress? We go all the way back to our phase understandings. What was the compressibility of liquids? Virtually nothing. I believe your textbook actually comes through and attaches a number to it. It's something like a 1% savings. Okay. So yes, it does technically save you money, but it's not really worth the extra effort. Okay. Last thing that we could address is the law of conservation of mass and energy. So we have rules or laws explaining that we can't destroy matter or mass, and we can't destroy energy. Well, Einstein was able to come along and notice that there was a direct correlation between these. Energy is related to mass, which means we actually have a law of conservation of mass and energy. I can convert mass into energy, and I can potentially convert energy into mass. Okay? That relationship is through his famous correlation, E equals mc squared, where E is energy, m, mass, c, the speed of light. Okay? Fun equation to play around with and run calculations with. Thankfully, we don't have to do it in this class. If you move into 151, you will use that equation and do a bunch of different calculations with it. Okay? So it's kind of a nice little process tied in through all of our scientific fields. Questions? Okay, let's see where that gets us. Oh, it gets us to a quiz. N is nitrogen, which I would write out. Yep, there it goes. Na. Tricky one, huh? I will accept another answer on the sodium one, and this really only came because I had a student from, I don't know where he was from actually, but not a native English speaker. I believe that's actually right. Natrium is actually a different language, but it is the origin of Na in this case. I almost took off points, but I was like, actually, I should take a look and see if that's actually true. Okay? And I think that was actually true. Br. Bromine. Nickel. Why would I ask the nickel versus nitrogen versus sodium? They've got a lot of N's floating in them. They're all very common elements to pop up. You will see those. You need to make sure you can keep them separated from each other. Silver. What do I give? Potassium. Okay, another kind of tricky one. Which phase has the highest kinetic energy? Our gas phase. I was about to say kinetic energy. Bit redundant. So our gas phase has the highest kinetic energy at any given temperature. In your opinion, what is the most important step of the scientific method? Anybody remember the steps of the scientific method?
I think it's observation and experimentation.
What do you think my opinion is of the most important step? Failure. Okay. That's the one step that everybody leaves out and seems to think doesn't exist. Failure is in 99% of all scientific methods. Okay? So that is going to keep coming back. You'll notice that is also kind of pseudo my teaching philosophy. I have a habit of breaking people, but I will help you get built back up. Okay? So take advantage of that help. I'm a little bit nicer in 130. Okay, so PSS, also known as Chapter 2 if you're using an older edition textbook. I have no idea what PSS stands for, actually. Cool. PSS stands for Prerequisite Science Skills. Neat. Did not know that. Types of measurements. Significant digits is the biggest aspect of the PSS chapter. Okay? And talk to anybody you want. Almost all of them will say, without a doubt, they hate significant digits. Okay? I tend to abbreviate it as sig figs for significant figures. It's pretty much the same thing. Along the line of significant digits, we get the carrying sig figs. And we'll talk about kind of why it's important to look at significant digits. And yes, it can be very counterintuitive to deal with these. Last one is scientific notation. Hopefully, most of this stuff is a review from your math class. I will say that I have not nice opinions about or how some of this terminology is presented in math classes. And you will hear about that when we really get into it, which is really the next chapter. I think I've got the homework scheduled right now for the PSS on the 4th. I'm not positive that's true. The 4th is like 2 days ago, or 2 days from now. I'll probably push that back.
When you open that, it says
I think it says the 5th.
Oh, I've already pushed it back? Okay.
Once you open it, it says the 5th. But if you look at the, it's kind of weird. Because it says, if you see assignments and due dates, it says September the 4th, but when you open it, it has a different date for the, once you open it.
Can you just tell us the
Yeah,
official date?
I'll tell you official due dates, and I'll try and post it to Canvas as well. Realize if I do push the dates back, that may not get announced. So go in, start your assignments earlier as opposed to later. I don't have any problems pushing due dates back a little bit up to a point. All of the material we're talking about now will never have a due date past what? Exam number 1. Okay? So absolute worst case, all of your homework will be due the night before exam 1, which is a horrible time to do it. So please do your homework before the exam to find out what's wrong, what you're missing, so that you can get that information reviewed for the exam. Okay? And if it's already doing weird due date stuff, I may just push automatically all the homework to right before the exam. Okay? As the default. Any objections to that? Oh, really? Okay. Go figure. Measurements. Okay, so we want to be able to take accurate observations, and we really want to be able to quantify them, okay, so that we can compare them to other things. So within individual measurements, we're going to end up with 2 separate components. Okay, there will be a number and a unit associated with it. Okay, that unit can sometimes change or be slightly variant depending on what we're looking at. So we want to make sure that we are as clear as possible within our measurements. So every time you supply a number, there's a unit associated with it. What if you've just counted something? Okay, let's see if I can do this without bringing the unit in. What am I holding up? Quantify it. What am I holding up? Quantify as best you can. There we go. Someone's actually breaking it down a lot more than I wanted you guys to do right away. Figured almost everybody would go after the pens. And what do we got? 10 pens. I would argue the answer that I was looking for is 1. Holding up 1 measuring cup. Okay? The number on its own is pretty useless unless you specify what it's in reference to. Okay? So what we've got here is 1 measuring cup and 10 pens. Okay? The unit is associated with that last part. It may seem obvious to you when you're stating it or when you're talking to someone, but when you take the test, you're not talking to anyone, theoretically. Okay? You have to write that information down so it is clear and understandable. So we've got a couple different ways that we can make observations. We've got distance and length, mass or weight, volume, and time. Try to put in bold the aspects that are more important. You'll probably hear me refer to distances as lengths, but they're ultimately the same thing. mass and weight are different from each other. Mass is something that is intrinsic to the molecule. Weight is what its mass is, or is its apparent mass in a particular location. Okay, so if we took our weight on Earth versus our weight on the moon or in space, we're going to get a different number. But if we take our mass, the mass stays constant. Okay, it has nothing to do with the relative location or gravity or outside features. Okay, so how do we get a mass then? Or a distance, or a volume, or a time? Give me a unit of time. Seconds. Okay, are there other units? Yeah. What are those units all based off of? Typically off of our seconds. So we have a base unit. How long is a second?
A second.
How did we decide how long a second was? What's that fraction of time? That is a human invention. Okay? How about volume? How do we measure volume? Any example units? Milliliters? Okay, liters, gallons? How did we decide what made those? How do we decide what a liter is? It's again a human invention. We came through and we came up with these definitive sections and said, this is what a volume unit is. Everything should now be measured off of this. All right. It would be nice if we were really consistent, right? And everybody used the same unit. Is that true? No. We've got metric. It's standard is the other term?
Yes.
Oh, God. Metric makes more sense. I don't like standard. That makes it sound like it's normal. Okay? So we've got all these different measurements that come off of it, which makes it more fun for students, because then what are you expected to be able to do? Convert between all of them. Okay? That conversion aspect is in this chapter. That's the next one. Okay, so let's come up with some base units that we would expect to see for each of these. And we'll address this again later in the semester. So what unit system do we want to use, metric or standard? Okay, metric. Most science is done in metric. You'll see engineers will pick up standard units, I believe. So I rip on engineers. Sorry. Okay. What's a base unit for distance or length?
Meter.
We get meters. Represented with what symbol? M. Why do we use a symbol? We don't have to write it out, which is all a fancy way of saying we're ultimately very lazy people. Right? What's our base unit for mass? This is actually an interesting one. The base unit for mass is a little bit odd. It is technically the kilogram. Okay? I, in reference to this class, will refer to the base unit as grams. Why? Because when we go through and start to move into conversions, and we talk about all the different ways that we can make these measurements in the different units, in the metric system, we can alter our base unit by putting in a prefix, okay, like kilograms. Okay, it works really well for distance, because if our base unit is meters, great, we get kilometers, decimeters, centimeters, millimeters. But when we go through, if we say the base unit for mass is kilograms, then it would be centikilograms, okay, which doesn't really make much sense. Okay? Why do we stick with the kilogram? We're going to look at a video or part of a video about that. It just happened to be with where mass was first defined. Mass happened to first be defined as a kilogram, and because of that, that is the official marker for mass. Okay? When it comes to unit conversions, the marker that we'll use would be grams. What unit do we use or symbol? Volume. We get liters. I think that's the American way, right? ER. And time. Time's a little bit weird. Okay. It is seconds, is our base unit. And we do use some of the prefixes, centi, milli, and all of that. but do we use that indefinitely? Do we ever get up to kiloseconds? What do we convert to? Minutes, hours, days. Okay. So we do end up tweaking out of our base unit a little bit. Okay. Most sciences, we're going to focus on that metric system. We don't want to scale outside of that. Okay. Oh, I think I got it a little bit later in. So measurements, we set a number and a unit. And the next thing we're going to try and touch on here is this uncertainty. Everybody hates uncertainty, and I agree with it. Okay? Because in the theoretical aspect, it is very difficult to nail down. So if we take a look at this rod, how long is it? I heard a, whoops, come back here. Well, we could zoom in a little bit. That's not too bad of a starting place. We could go through and say it's 4. Right? But is it exactly 4? No. Okay, but there aren't any markings in that space. So how do I know what to put as the next number? There it is. Fancy way of saying it. Estimate, also known as guess. Okay, it's an educated guess, but that's what we're doing. So we could go through, and I heard someone say 4.2. I heard a 4.25. Anything else? Is it really a quarter? I think that's probably 4.3. Okay, any other guesses? What's the uncertainty? Well, the uncertainty is that we took this rod, and we took it away from everybody else, so nobody else influences the decision, and we give them the ruler. We've got these 1,000 people, and we tell all those 1,000 people to tell me what that measurement is. Okay? Then what I go through and do is I look at all of the measurements that people gave me, and I look to see how far off they spread from the average. Okay? Once I see what that spread is, what I'll do is go through and then say with this measurement that this is actually 4.25 plus or minus 0.1. We don't have a unit on this, do we? That was nice. Let's call it centimeters.
It's underneath the.
Oh, where?
You're going to take off the other.
Oh, I've blocked it. Okay. And we now have our measurement written out, and we'd include this uncertainty with it. Okay. With that uncertainty, does it make sense to include the 5? Why? The closest I can measure it is to the 0.1, which means including that 5 is not just an educated guess. That's out of left field ballpark. I have no idea what I'm saying. Here's a random number, 5. Okay? I don't want to include that because I don't have the accuracy to that decimal. Okay? For that very same reason, I would not write the distance of this was 4.2016389 plus or minus 0.1 centimeters. Okay? All of those numbers I just made up. Okay? The instrument doesn't give me that accuracy, so I can't report it to that accuracy. All right? If we go through and add another little marker, oh, good guess on the 4.25. Okay, we could add some more markings into that, and now we could read a little bit further. So instead of saying that first measurement was just a 4.2, we could now look a little bit closer and say, yeah, it definitely hits the 4.2, and it's definitely not at the 4.3. So now I know for sure that that 4.2 is correct. Now I have to guess. What's the guess digit? You guys like the 5? Let's stick with the 5. But now my uncertainty would be plus or minus maybe 0. Oh, darn it, I'm out of space. Plus or minus 0.03 or 1. How do we know what that number was? We took that measurement thousands of times by independent observers to nail down exactly what we're reading out of. Okay? So when someone asks you for what the uncertainty is in a measurement, you're looking at these rough approximations and then kind of guessing. That last digit that you guessed is your uncertain digit. Every measurement includes that uncertain digit. Okay? We need a little bit of guess because that gets us a little bit more information out of it. Okay? That said, when we go through and report a number, the uncertainty should always, always, always be reported with the measurement. Walk into pretty much any class you like as far as where they take measurements, and what are you going to find? How often is the uncertainty reported? Outside of lab number 2 that you guys will do this semester, you will probably never record it again. Okay? Is that good scientific technique? Absolutely not. But what we start to imply is the accuracy of our instruments, and we tend to trust them a little bit and carry out what they repeat to us. Okay? So be aware that it is an important thing to acknowledge the uncertainty. And if you ever have to go through a publication process, you do have to report that uncertainty. And it sucks, particularly when you bring in significant digits and how you have to translate that uncertainty through a sequence of calculations. Okay? When we get into mass, the mass of the object is independent of gravity. Okay? So it's the mass of the matter that is contained within it. The only way we can really determine this is through a balance. Okay? We put our defined mass, this is a kilogram, on the right-hand side, and on the left-hand side we mass whatever else we want to add. And it's the comparison between this is a kilogram to whatever we're measuring that allows us to determine what the mass is of an individual structure or object. Okay? So mass and weight are not officially interchangeable. Okay? So when you refer to it, try to always refer to it as the mass. You may see me give you a hard time, but probably won't care that much. Okay? So where did the mass come from? We got another fun little link, which is actually not in the slides, unfortunately. That was kind of my fault. Let's skip the ad. I do not support anything that was in that ad, whatever it was. Oh, come on. Now I'm going to go right back into the ad, aren't I? Okay, well, let's pause this. Well, we won't pause it. They're going to give me the opportunity to skip it. And I actually want the audio for this. This is actually kind of a neat video. Sorry, brought that in a little early.
Can I hold it?
I think you promise to be really, really careful.
I promise I will be so incredibly careful. I will be incredibly careful.
Okay.
I promise.
All right. So it's slippery. Be careful.
All right. Are you ready? I'm about to touch a 1 kilogram sphere of silicon-28 atoms. They're about 2.15 times 10 to the 25 of them. It feels absolutely incredible. Wow, that is amazing. Besides its creators, I am one of only a handful of people ever to hold this sphere. The raw material used to make it was worth 1 million euros, but now that it has been so precisely sculpted, how much is that worth?
It's priceless. This you're looking at now is the roundest object in the world.
How can you say for sure that it's the roundest object? I mean, the Earth is pretty round, isn't it?
If this was the Earth,
If this were the Earth, then the highest mountain and the lowest valley would be...
about 14 meters apart.
That is shocking. That is shockingly round. But why would you invest 1 million euros and thousands of man-hours perfecting a pure, polished silicon sphere? Well, the answer is great.
Or rather, grav, as it would have been pronounced in the original French. You see, the grav was the original name for the base unit of mass in the metric system, which became the System International d'Unité, or SI units. In 1793, a commission, which included notable scientist and aristocrat Antoine Lavoisier, defined the base unit of mass as the weight of a cubic decimeter of water at the melting temperature of ice. Essentially, just a liter of ice water. The name grav came from the Latin gravitas, meaning weight, but it wasn't to last. It sounded too similar to the aristocrat title graf, which is the equivalent of an earl or a count. And with the French Revolution in full swing, with the rallying cry of equality for all,
Okay, we'll pass on the rest of that history. But anybody kind of get at what that sphere measures? It is now the standard SI unit for a kilogram. They invested millions of dollars to make 1 kilogram, okay? To make the perfect kilogram so that it accurately represents what we can then compare everything to for our mass. Okay, so it's kind of neat. We came up with the mass unit by measuring those distances and saying this is now the mass of water, and I'm going to define this mass of water as my base unit for everything else. Okay? Kind of a neat process to go through and observe, at least in my opinion. Okay? Agreed? Some enthusiasm. Why do they use silicone? I believe it's because they can easily mill it and then it stays constant. It doesn't have a lot of volume changes associated with it, and it's relatively stable. You could go through and do something like gold or platinum, also relatively stable, but then also relatively really expensive. And probably in the milling process, you're going to end up chipping more of the gold or platinum off. The silicon's probably a little bit more stable for that milling process. Would be my guess. I'm not a materials engineer, so I'm not sure.
Why is it so expensive to take that?
It has to be a single crystal. So when you look at that mass, it is exactly silicon, atom by atom, in its exact perfect crystalline structure. And if you think about why solar cells are so expensive, it's because it's not easy to make silicon in perfect crystal alignment. And we end up with different types of silicon cells, amorphous silicon. Why? We lose some of the efficiency of that electric transfer process, but it's a heck of a lot cheaper than making the single crystals. Okay. Other questions? Okay. Volume measurements. We got a variety of different instruments to go through and make volume measurements. They're all pretty much based off of the liter as our base unit. What's the most common volume that you think you'll be dealing with this semester?
Milliliter.
Why milliliters and not liters?
Because it's smaller.
Why is smaller better in this case?
More accurate.
I don't think you're getting an accuracy issue out of this. In fact, if you make a small measurement error in a milliliter versus a small measurement error in a liter, the milliliter is going to mess up more frequently. You're going to have more error introduced. The liter, because it's so much larger, a small measurement error isn't going to make a big deal. If I walked in here with a liter of concentrated hydrochloric acid versus 1 milliliter, okay, it's a safety issue, is really it. Okay? We don't want you working with things on the liter scale because if anything goes wrong, that's a pretty big mess to clean up. Whereas with the milliliter scale, oh well. You spill a little bit, we add some water, throw some salt on it, and everything's good. Okay? So it's really just a scale of safety. 40, right? Well, we'll probably end up talking a lot about significant digits, so we should probably get into it. So, when we go through and report a measurement, we need to have some understanding of what the digits are within that and whether they are important or not. So when we measured out initially our 4.256842139.7. What's the next digit?
3.
Sure, I'll accept 3, just because you're the first one. Was there an actual pattern that you saw? Okay, just curious. Plus or minus 0.1. That's a number without a unit, so let's throw in a unit, centimeters. Of those digits, which of those are significant?
First
4.2. Why? It has to do with my uncertainty. I can only accurately measure up to the plus or minus 0.1. Right? Which means the only digits that I can use are going to be those first two. The rest of those are just made up numbers. Okay? So our significant digits are going to come off of our measurements, and when we use our measurements, the instrument will tell us what our significant digits are, and we report them as is. Okay? Plus whatever that guess number is, okay? Which will be apparent when you look at the instrument. Okay? when we look at that last digit, that's where our uncertainty kind of comes into play. So the last digit in our number here was our 4.2. There's our kind of uncertainty measurement. The rest of those numbers we just made up, and we'll ignore those. All right? So how can we decide if we don't have an instrument what makes the digit significant? All right, that becomes a little bit trickier. Let's say I don't give you the uncertainty. What digits are significant?
First two. 4.25.
Without the uncertainty in there, we don't really know. Okay? So if when we go through and make our measurements, we never report the uncertainty, we have to have some understanding of looking at these raw numbers and saying what makes a digit significant. Because like I said, we aren't going to be reporting that uncertainty. All right? So let's take a look at significance. Digits 1 through 9 are always significant. They always carry a value associated with them. Right? So you have to always include them as a significant digit. All right, that's not a bad rule, except does that cover all of our numbers? What if I threw the number 10 at you? Or the number 0.1? We do have the 1, but we also have the 0 in there. So now it's a question of do we count the 0 or do we not? And that becomes a lot trickier. And that's really where our significant digits pop in. Right? To decide whether the 0 is important, we have to know more information. That more information is the decimal point. Okay? An incredibly useful piece of information that is usually relocated to a random dot on the paper. Okay? So let's take a look at these numbers that are listed out here. How many significant digits in that first number? 1. Next number. Next number. Next number. Last one. Well, now that you guys know all the rules, we're just good to move on, right? Any questions? No questions. You're happy with that? That's all you need to know about significant digits. No, you should be upset. We need to come up with some rules on what makes each of these digits significant and how we count them. Okay? In all of these cases, what we're looking at is the 0. When do we count the 0? Okay, well, the 0 holds two important definitions when we look at numbers. The 0 can act as a placeholder, in which case it has no meaning beyond the fact that it's holding a place. Or it can mean the complete lack of another number. Well, if it's acting as a placeholder, it's not a significant digit. If it's acting as the lack of another number, then it's a significant digit. That clarifies it, right? All the numbers make sense now? Okay, some no's. I can accept that. Let's go through and look at a different system. If there is no decimal point, okay, then our 0 must be controlled by numbers to either side of it. Okay, so our numbers can almost act as a decimal point. So if we have no decimal point and a 0 is in the middle of a number, then it counts as a significant digit. Okay, so in that first case, we have one significant digit as the 1. Should have changed the numbers a little bit. And a second significant digit as the 2. Since the 0 is controlled, if you will, by a significant digit to either side of it, that counts as a lack of a number, and we're looking at a third digit. There are 3 significant digits in that first number. Okay? What happens in the next case? We've got 1 and 2, which are absolutely significant digits. We have to count them. For the 0 to count, it must be controlled by numbers to either side. Okay? Well, if we look at that 0, yes, it is controlled by a number to its left, but is there anything to the right? Nothing there. The 0 does not count as a significant digit, and what we have for our numbers of significant digits, 2. The 0 is acting as a placeholder to push the 1 and the 2 forward. Okay, to put the 1 in the hundreds place and the 2 Tens? Tens place? Is that right? It is tens, isn't it? Thanks for the feedback, guys. I wasn't asking because I'm trying to be a jerk. I don't know my places very well. Okay. What happens with the next number? We have the 1 and the 2, so it's actually 2 sig figs, but our rule so far, our rule number 2, was that no decimal point. Well, I do have a decimal point here. Okay, so we need a new rule. That's rule number 3. If there is a decimal point, then the 0 needs to be preceded by a significant digit. There must be a significant digit in front of it. So we go back to our 0 and say, there's my decimal point, and there's a significant digit in front of it, which means how many sig figs? 3 sig figs. I think I heard someone say 4. Okay, for it to be 4 sig figs, what do I need to have? I need another number in this circling was a bad option. I need another number there. There is no number written there. If there is no number, I can't have a 4 sig fig. Okay? The decimal point is to define the 0 in front of it as our sig fig. It is not being used to add an extra number. Okay? How about the next one? One and 2 are sig figs. Okay, now we got a bunch of zeros. So let's start. We'll go left to right. First 0. I have a decimal point, so all I got to do is look, is it preceded by a significant digit? Yes. So what does that mean that 0 is? Significant digit. Move to the next 0. What's in front? I'm hearing zeros, but let's change that up. It's not a 0 anymore, it is a significant digit, which means that 0 at the end is also significant. The number of significant figures? 4. Yeah. Okay. Let's go ahead and let you run through the right-hand side. Feel free to talk to the people around you. We will be kind of ending with doing those. So if you've got questions, raise your hands. I'll give you 2 to 3 minutes, and then I'll write up the answers for each of those. Let's go through and tag these out real quickly. First one, the answer is 2. Good. Second one? 2. Next one? 2. Last one? 3. Okay, a couple things to address before we go. What is the difference between these two numbers?
The 0.
As far as the number goes, they are the exact same. Why would we represent one versus the other? When you make a decimal point, what do? What's your gesture? You can make the gesture, that's fine. You can do it up in the air. Writing a number. I'm writing 0.12. What's the issue with that point? It's very easy to lose when you are manually writing a number. If you include the 0 in front, worst case you look at it and go, why the heck is there a 0 here? That doesn't make sense. If this is 12, why do I need a 0? Oh, there's a decimal point. If you don't have the 0 in front, very easy to lose the decimal point, and your value that was 0.12 becomes 12. That's a pretty significant difference. Okay? So what you will see, at least if I write on your papers, is something known as this. Leading 0. And it serves no other purpose than to just mark that you have a decimal. That's all that's there for. Okay? Why is this 0 not count? Following rule number 3, there is no significant digit in front. Does not count. Next number. Okay, start left to right. Is there a significant digit in front? No, which means that 0 is not significant. We move to the next 0. Is there a significant digit in front? No, which means not significant. We're left with 2. It's not lack of a number in those cases. What are those zeros representing? And I'll end it on this. These zeros are placeholders to tell us that the 1 is in the hundredths place and the 2 is in the thousandths place. Wow, you guys know that a lot better than me. It's kind of scary. Okay, we'll start again with those same sequences on Thursday, and then we'll get into the